All right, hello everyone. For today, since we're done with our specific review, we're just going to be doing mixed review problems. This is what I recommend. If you're feeling comfortable, you can try the problems here. Do read if they're labeled A, B, B, C, or just B, C. You can try the problems and come back and correct your answers, or you can work along with me and take notes and then try the homework ones. Either one works for me. I've had bad luck with my recording, so this is the second time that I've done this already. So I will hopefully be pretty good at this and it'll move a little quicker. All right. So we're given this continuous function on the interval -4 to 6. It consists of a line and a curve that's tangent to the x-axis at x equals 3. So we have a point right there. And we know it's twice differentiable from 0 to 6, with the second derivative being greater than 0. If the function is differentiable, is the function differentiable at x equals 0? Well, looking here, it looks like the answer is going to be no, but they say use the definition of the derivative with one-sided limits to justify your answer. Definition of derivative with one-sided limits to justify your answer. Well, it looks like we're not differentiable there because we have a corner or cusp, but we need to show that using the definition of a derivative. So to show that there's a corner, basically we need to show that the slope from the left and the slope from the right are not equal. So I could say the limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0, I just need to show that that is not equal to the limit from the right of the slope. Because really, for differentiability, all we need to do is check that the slope from the left and the slope from the right are not equal. That's what we actually are doing when we talk about something being a corner or a cusp. We're really talking about the slopes from the left and the right not being equal. So I can go ahead and write that. The limit as x approaches 0 from the right, then, of f of x minus f of 0 over x minus 0. That these two things are not equal to each other. I've used the limit definition of a derivative to justify why this thing is not differentiable. If you would like, we can actually find the slope from the left. The slope from the left there is actually 2/3. And it is not going to be equal to the limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0. So is it differentiable? Then we can say since the two-sided limits, the one-sided limits do not agree, since the one-sided limits do not agree, f is not differentiable. At x equals 0. There we go. All right, 1 point for setting up the difference quotients, 1 point for your answer with justification. All right, let's move on to part B. Part B, for how many values of a on the interval -4 to 6 is the average rate of change of f on the interval a to 6 equal to 0? So I see an average rate of change question. You definitely just need to write down your average rate of change formula for that interval. The interval is a to 6. So I could say f of 6 minus f of a over 6 minus a. And I want to know for how many values of a, which is between -4 and 6, is this average rate of change on that interval equal to 0? Setting that up gets you 1 point. Now I got to figure that out. I want to figure out how many values of a is this average rate of change going to be equal to 0. Well, if the average rate of change is equal to 0, that means the numerator is equal to 0, right? If the numerator is equal to 0, that means f of 6 equals f of a, right? So what is f of 6? F of 6 is 1. So in other words, I want to figure out, hey, how many times, for how many a values is f equal to 1? For how many a values is this function going to be equal to 1? Oh, that should be continuous there. Equal to 1. It looks like twice. There's two places where f of some value here, some x value equals 1. There's 2 times. So I'll say there are two values of a for which this is true. Okay. There we go. 1 point for your average rate of change expression, 1 point for your answer with justification, which your justification can involve this work here. Okay. We keep going. What about question C? Question C here. Is there a value A on the interval -4 to 6 for which the mean value theorem applied to that interval guarantees a value in that interval, C, for which the derivative at C is 1/3? Justify your answer. Well, we know for the mean value theorem, right? For the mean value theorem to apply from some A value, I don't know, A could be out here, until 6, that to use the mean value theorem, the interval needs to be differentiable and continuous, right? So I can't include, if my ending value has to be here, and I'm back in this direction, I can't have A all the way over here because I have a corner. So I got to be at least on the other side of this corner, right, to use my mean value theorem from here, from A, wherever A is, until 6. All right? And for the mean value theorem, whenever we do the mean value theorem, we need to set up a difference quotient. So the mean value theorem always says that, hey, there's a place where the average rate of change on that interval equals the derivative at some spot. And they're saying, hey, is there a value where the derivative is going to be equal to 1/3? So basically, if the mean value theorem applies, this average rate of change has to equal 1/3, and A, wherever that A value is up here, has to be starting at least here on this side of that corner there. To be able to use my mean value theorem, I need a differentiable section. So wait, let's just think for a second then. Okay, I got to be over here somewhere for my A value. And I need the average rate of change to be positive 1/3. Well, if I started here, that'd be a negative slope. I don't know any of the points along here, so let me just use the other obvious point here. What about when x is 3? Let me find the slope there and see if it's going to be 1/3. So if x is 3, I'd have f of 6 minus f of 3 over 6 minus 3. F of 6 is 1. F of 3 is 0. 6 minus 3 is 3. So look at that, 1/3. So cool, I think I just found it. The value of A needs to be 3. That needs to be my interval. That if I apply the mean value theorem on here, it'll work because it's a differentiable section of the graph. There is going to be a place on that interval where the derivative is 1/3. So now I just got to write that stuff out. So they say, is there a value? Yes, A is 3. Then I can say all my mean value stuff. F is differentiable, I'll abbreviate it, on the interval 3 to 6. And you technically got to say it's continuous on the closed interval. I guess I could say differentiable and continuous on the closed interval there. So sorry about that. Differentiable on 3 to 6 and continuous on the closed interval 3 to 6. F of 6 minus f of 3 over 6 minus 3 equals 1/3 by the MVT. There is a value C, and you just kind of restate. There is a value C on 3 to 6 such that f prime of C equals 1/3. Well, you got 1 point for saying yes and A equals 3, and then 1 point for your answer and justification. Your justification here. Okay, let's take a look at part D. The function g is defined by this integral. On what intervals contained from negative 4 to 6 is the graph of g concave up. So I could say g is concave up when g double prime is positive. So we find that. So g prime of x, I know g of x is this integral, so the derivative of this integral is going to give me f of x, because I'm just going to sub in the endpoint. If the endpoint had been something other than x, like 2x, I would have had to say f of 2x times the derivative of that upper boundary, but it's a simple accumulation function. So that's that. Now I need the second derivative of g, which is going to be f prime of x. If it helps to write you a note, you can say f prime is the slope of f, to write a note to yourself, and that's what I need to look for. All right, you get 1 point for saying the derivative of g is f. You get 1 point for considering looking at the second derivative being greater than 0, and then our answer, I can say g double prime of x equals f prime of x is greater than 0. So I need to look for where the slope of f is greater than 0. So that'd be negative 4 to 0. And where else is the slope positive? 3 to 6. And there we go, 1 point for your answer here, these intervals. All right, so there's the first problem. As we continue, remember you can do the problem yourself and then come back and check yourself, or you can work along with me for these practice ones. Next problem is also an AB problem. We're given the velocity of a particle moving along the x-axis, modeled by a differentiable function here, where x is measured in meters, t is measured in seconds, the selected values of v of t up here. We're also told position at x equals 7 when t equals 0. That sounds like an initial position, so I'm just going to kind of make a note of that. Probably going to be useful. Estimate the acceleration of the particle at t equals 36 seconds. So we need to show the computations and indicate units of measure. Acceleration, that's the slope of velocity. I'm given velocity. 36 seconds is right in here. I don't have that time, so I can take a slope formula thing of velocity to estimate that acceleration. So a of 36 is going to be approximately v of 40 minus v of 32 over 40 minus 32, which is going to be v of 40 is 7 minus v of 32 is negative 4 over 8. I want to put units on this now since they did say I need to indicate units of measure. My velocity units were meters per second. My time units were seconds. We could actually just leave it like this. We don't have to do anything fancy, or we don't need to simplify stuff or do anything that might accidentally cost us a point there, remember? So we can leave it like that, or you can simplify it down to 11/8 meters per second, or meters per second squared. You get 1 point for your answer, and you get 1 point for getting correct units in A and B. So let's actually do B. Using correct units, explain the meaning of this integral in the context of the problem. So this integral, 20 to 40, if we took the antiderivative velocity, we'd get position. Then we would plug in 40 and 20. So it would give us the change in position from 20 to 40 seconds. But that's change of position. We also call that displacement. So you could say that this is our displacement or change of position formula. So this integral is the change in position. We also always want to indicate units. Change in position, you have to indicate units in meters because our velocity was meters per second. So it's the change in position in meters of the particle then we have to always go to the time or the interval or whenever it's happening. So the change of position meters of the particle on the interval or from 20 to 40 seconds. There we go. So that's 1 point for the meaning, getting all that stuff. You got to get units, both units, and then what we're actually measuring, the change in position. Then it says, use a trapezoidal sum with 3 subintervals indicated by the table to approximate this interval. So we only want to go from 20 to 40. So we have 1, 2, 3. That's why I said 3 subintervals right there. So this integral, 20 to 40, that integral is going to be approximately, to do a trapezoidal sum, we look at our first interval, we add together our output values, negative 10 minus 8. We multiply by the delta t or delta x, the width of the interval, which is 5, over 2. Plus, then we look at our next interval. We add together the output values, negative 8 minus 4, times the width of that interval, to go from 25 to 32, that's 7, always divided by 2. Plus my next interval, we add together the output values, negative 4 plus 7, multiplied by its delta t, which is 8, over 2. So there we go. That is our trapezoidal sum. You do not need to simplify, but just to be safe, we could slap meters on here since we are measuring a change in position or approximating a change in position. If you do simplify, you get negative 75 meters, but why would you bother? We'll just leave it like this. All right. Cool, we're chugging along. 1 point for the meaning of this integral, 2 points for the trapezoidal approximation down here. Okay. Let's keep chugging ahead. C. For 0 to 40, must the particle change direction in any of the subintervals indicated by the table up here? If so, identify the subintervals and explain your reasoning. Well, a particle changes direction, right? If I'm given velocity, I know a particle changes direction when v of t changes sign, right? Something like v of t is positive, positive, negative. So I have a sign change there. Then I have a sign change here as well, right? So what do I know? I know v of 8 was positive, and v of 20 is negative, and I know v of, what's my next interval? V of 32 was negative, and v of 40 is positive. Right, I know those things. And, well, to be able to prove that we're changing sign by just looking at signs, we need to be able to use the IVT, right? And V is differentiable and continuous. Therefore, by the IVT, the particle changes direction twice. Once on 8 to 20 and once on 32 to 40. All right. You get 1 point for your answer because they ask for 0 to 40, must the particle change direction? So I answered that. The particle changed direction twice. And if it does, identify the subintervals. The subintervals are 8 to 20 and 32 to 40. So I identified that. So you get 1 point for saying yes and identifying your intervals and then your explanation. My explanation was, hey, V of 8 was positive, V of 20 was negative, V of 32 was negative, V of 40 was positive, and V is differentiable and continuous. Therefore, by the IVT, the particle changed direction on those intervals. There we go. Now, I really like question D. Suppose the acceleration of the particle is positive for 0 to 8. Just this interval right here. So we ignore all this other stuff. All right. if the acceleration of the particle is positive, so if a of t is positive, what do we know? Well, if a of t is positive, v of t is increasing. I'm just going to write myself notes. I've not even looked at the problem yet. But I do know that. If a of t is positive, v of t is increasing because a of t is the slope or the derivative of v of t. So let's read. Explain why the position of the particle, so now they're asking me about position, at t equals 8 must be greater than 30. Well, if I know that velocity is increasing because a of t is positive, that means my minimum velocity has to be 3 because I know velocity is increasing, so 3 has to be my minimum. So I can say v of t, just to write myself notes, v of t is greater than or equal to 3 on 0 to 8 then. Okay, so what? Well, I need to know something about position at 8. Let me just write down what I know. If I want to know position at 8, what do I know about position? I know my initial position. I know x of 0. And if I want to know the position of 8, that'd be the integral from 0 to 8 of v of t dt. And I want to prove that the position has to be greater than 30. So let's see what we can do. I know x of 0 is 7 plus the integral from 0 to 8. Well, what do I know about velocity? I don't really know, but I know that if it was bare minimum, if this thing was moving as slow as it could, it's got to be at least moving 3. Velocity is at least 3 because velocity is increasing this whole time. So let's assume velocity is the smallest thing possible. Let's just assume velocity is 3 and see if we get above 30 meters, because if we do, then great. We definitely hit the 30 meters. So let's see, that'd be 7 plus the integral from 0 to 8 of 3 is 3x. We plug in 8, but we have a shortcut for that. It's 3 times the difference, 8 minus 0. You could do your FTC, take the antiderivative. That works too. So that's 7 plus 24, which is 31. Therefore, x of 8 must, must be greater than 30. There we go. You get 1 point for making this understanding here. You could have written just the v of prime of t equals a, or just written out that a of t is greater than 0, so v of t is increasing, making that connection is a point, and then doing your work to explain that x of 8 has to be greater than 30. All right. So that takes care of the AB problems. If you're an AB test taker, you can now jump past the next one and get started on the homework. For your homework, you're doing normal, do the FRQs, score, make corrections, but just for the first two for your response questions in the homework section. BC people, we got one more example here. I like this problem a lot. It does stretch a few things that you don't need for the test, but are stuff that you should be able to handle at this point because we have talked about some things not on the test. All right, real quick here, the function f is defined by this power series. So f, whatever the function is equal to this infinite series, which is equal to this sum for the real numbers on which it converges. Find the interval of convergence for the power series for f. Justify your answer. Well, here's what I like about this function. This function here looks a whole lot like a geometric series, right? A geometric series is very simple. It's some number times some number to the n. And it looks like if we compare these two, a would be 1, my r value would be equal to x plus 1, and I have a geometric series that I can work with. All right, I should have written this down here to be a little more clear, but to save time, we'll leave it up there. All right. Now, what do we know about geometric series? This thing looks like it's kind of we're forcing it to be geometric. If it's going to converge, that r value, a geometric series converges. So I can say, let's start doing some work down here. The series is geometric. That actually gets you 1 point just for saying that. Series is geometric. And now, if the series is going to be geometric, I need to do some work with it, and I want it to converge. The series is geometric. I know a geometric series converges if the absolute value of r is less than 1. So I can say the series converges if r, though, we're saying my r value position thing, my thing with the n is x plus 1. So the series converges if the absolute value of x plus 1 is less than 1. So you actually get 1 point for saying that. Because my x plus 1 to the n, that's in my r position. That's my ratio, common ratio. So then what do I do with this? I'm trying to find the interval of convergence. So this is a statement, but the interval of convergence, I need to turn this into a compound inequality, get rid of the absolute value bars, and I get negative 1 is less than x plus 1 is less than 1. Subtract 1 from both sides. So my interval of convergence is actually negative 2 to 0 is the interval of convergence. So part A is not actually something that would really be on the test this year because interval of convergence, radius of convergence is not really a thing, but we do know geometric series, so you might have some similar kinds of things around doing some work with geometric series. Again, we recognize this as a geometric series because we have a times r to the n, and we can use all of our geometric series stuff. In fact, we need to keep using that. So you get 1 point for saying it's geometric, 1 point for writing out that statement, and then 1 point for your interval of convergence. Now, I'm not going to erase everything because part B still uses this idea of geometric series, which is on the test this year. The power series is so they're saying this series here is the Taylor series for f about x equals negative 1, but that makes sense because it's the x minus c, so x minus negative 1 is a Taylor series. Find the sum of the series. Well, sum, I really don't know how to do sums if I have actually find an infinite sum if I have a geometric series. That's really all we've learned how to do right now. But wait a minute, we've already said this series is geometric. So what do I know about the sum of a geometric series? Because I know f is this power series, which is the sum, and I know how to find the sum of a geometric series. So the sum of a geometric series is the initial term over 1 minus r. All right, what's my initial term though? It's 1. A is 1 because I don't see it there. I kind of wrote it in. So what is my sum? The sum from n equals 0 to infinity of x plus 1 to the n. I know this is geometric. The initial term is 1 over 1 minus r, but r is whatever in the parentheses to the n. So it's really 1 minus x plus 1. I could actually leave it like that if I wanted to, but I can simplify that to 1 over 1 minus 1 will go away, so I get negative x. And there we go. There is my sum. Technically, this is on the radius of convergence if x is between negative 2 and 1. Sorry, 0. So I actually get 1 point here for this answer. 1 point for this answer, and that's it for recognizing, hey, this is geometric. The sum of a geometric series is initial term, which is 1, over 1 minus my r value. So there we go. Okay, let's just do part C right now too. Part C, let g be the function defined by this thing. G of x is the integral from negative 1 to x of f of t dt. F of t dt. So I could write f, so f is this. I could write an infinite series. That would be a lot. I could write this, but it's a pain to do that. But what did we just find out f is equal to? We just found out that this series is actually equal to just negative 1 over x. Oh, sorry. In this case, I guess t. Right? So I'm actually just going to leave it like that. All of these things are equivalent. That's the beauty of these series, that f of x is this infinite series, which is this sum, which happens to be geometric, and I found out that that sum is 1 over negative x. Cool. So all I did was, if I'm taking the integral of f of t, I just plugged in what I found out the sum is, negative 1 over t. There we go. So what are they asking me to do with this? Find the value of g of negative half, if it exists, or explain why it cannot be determined. So I want g of negative half. That'd be the integral from negative 1 to negative half of 1 over t dt. That looks like an integral I can do. The antiderivative of, negative. The antiderivative of negative 1 over t dt would be negative natural log of the absolute value of t. Notice the negative is just constant multiple, so I pulled it out, and then the antiderivative of 1 over t is natural log of absolute value of t. Evaluate from -1 to -half. So all I have to do is plug that stuff in. Negative natural log of the absolute value of -half. Ooh. -half minus the quantity when I plug that in. So minus negative natural log of the absolute value of -1. There we go. So this would be my answer. You can clean that up if you want to, but why bother? Let's just leave it like that. You get 1 point for your antiderivative, and then 1 point for your final answer. Again, the trick here is that we're trying to find the integral of f. F is this complicated thing. It's a sum, it's a geometric sum, which in part B I found was actually equal to 1 over -x. There we go. So I can plug it in for f because it's equivalent. This stuff equals -1 over x on this interval of convergence. So it is f of t. All right. And part D. Part D says, let h be the function defined here. Find the first 3 non-zero terms and the general term of the Taylor series for h about x equals 0. Well, I know that h of x is equal to f of x squared minus 1. So basically I can take f and plug in x squared minus 1 for all the x's. So I go to my first term, that'd be 1, plus I go to my next term for f, I plug in x squared minus 1. So x squared minus 1 plus 1 will simply leave me with x squared. Plus, then I substitute x squared minus 1 in for my next term. X squared minus 1 plus 1, the 1's cancel out, I get x squared squared. So x to the 4th. And I could keep this pattern up, right? But all they wanted was the first 3 non-zero terms and then the general terms. So I go to my general terms, that'd be plus. I'm going to, again, h is f of this stuff, so I'm going to plug this stuff into f. So x squared minus 1 plus 1, the 1's cancel out, so I end up with x squared to the n. So that's x to the 2n plus dot, dot, dot. There is my h of x function. I have the first 3 non-zero terms and the general term. So I've actually gotten 2 points already. First 3 terms and the general term. Now this is interesting. I want to find the value of h of half. Not approximate it, but actually find it. H of half. So h of half, if I go in here and I plug stuff in here, would be 1 plus half squared is 1/4, plus half to the 4th, that's 1/16, plus and so on and so forth, right? So let me see, is there a pattern I notice here? Because I actually want the value, not approximating it, I actually want the infinite sum. Well, how do we get an infinite sum? If it's geometric, it's easy. So to get there, that's a factor of 1/4, 1/4, aha. This is a geometric series. This is a geometric series with a is equal to 1, that's my starting term, and r is equal to 1/4. So my sum, if I continue this, by plugging in half all the way to infinity. Since it's geometric, it will converge, since r, the absolute value of r is less than 1, so it will converge to the sum I used earlier, the initial term, which is 1, over 1 minus r, which is 1/4, because I found we're multiplying by 1/4 each time to get up to the next level. So this is my value for h of half. The exact value of h of half, by plugging into this infinite series, is a geometric series, I identified r, and the initial, it will sum to this. And I'm done. That's my last point. All right. Hopefully this helps get you started. For homework for tonight, if you're an AB test taker, you gotta do the first 2 FRQs. If you're a BC test taker, you gotta do the last 3 FRQs. You can do that first one if you want, but you do not have to. I'll post answers and things later. Other than that, be sure you score yourself and be on the lookout for office hours and things. All right, take care, everybody.